Good morning, everyone. I'm going to give it just a few seconds for people to come in, and I'm going to get started. We've got a lot of material to cover today, so just bear with me. I've got this recording. Okay, about one more minute, and I'm going to go ahead and get started. All right. Let's start out with a short survey.
You had to do that?
Make it anonymous. And answer honest, it's anonymous. I'm just curious. All right, so I'm going to give everybody just a second to answer that while the last people come in, and then we will get started. Okay, we're going to go ahead and get started. All right, so I see from the poll, 5 people said yes, 2 people said some of them, 1 person said no. I'm disappointed I didn't get any what videos. looks like one person in here maybe hadn't answered. So if you hadn't answered, yeah. Thank you to whoever changed it to that. So this week I've explained it to everybody in my PM group, but I know that I have some people in here that are in other PM groups. I don't know if everyone is totally informed of what's going on this week. What the deal is that you're going to have 2 days of GP and independent project. You'll have a third day in the morning with us and possibly the instructor. And then at 11 o'clock on Wednesday, you will receive your sprint. You will have until 11 o'clock Friday morning as usual to complete it. And then the rest of the day per the usual protocol. If anybody has any questions or isn't aware of this, has any questions about it whatsoever, unmute your mic and ask to save time.
So the sprint challenge is 2 days?
Yes, sir. The sprint challenge is very doable. Originally, it was given as the regular 3 hours. It's using the stuff that we're working on this week and the stuff we're going to start going over today, graphs. It's going to be a traversal over a maze, and you've got to get your traversal under a certain number of steps to be MVP and to be stretch. So it took too long to be a 1 day. So it's indeed 48 hours, basically. Does that explain your question?
Yeah,
it's hard. It's hard. I'm not going to lie. I told everybody straight up in my reviews the other week on Friday that it's difficult. It's very doable. Everybody should pass it, but you don't want to put it off until Thursday night. Trust me. It's something that you need to, okay, well, I've got X amount of days to do it. I'll take this on, day 2 or the night of or whatever. Definitely get on top of it. So we've got a lot of material to cover in the next 2 days and a lot for your independent projects, but that's how the people way above me laid it out. So I'm just here to kind of present what they give me to present. Anybody else? All right. Give me 1 second. I'm going to close my door and I will get started. Okay, can everybody hear me okay? The screen share's transmitting good. Somebody answer in the channel because I can't. Cool. All righty, well, we will get started. The rationale behind this module, behind graphs, is that they are a very powerful and diverse data structure that represent relationships between data. They can be used to represent anything from a social network, web page, site maps, flight patterns, user behaviors, and much more. The take home from this is if you have relationships between data, you can build a graph and utilize operations like a breadth and depth first search that you have seen videos over and that we will cover more in depth with the live coding to gain a really powerful insight into them. You're going to see a lot today. You're going to come across a lot in your guided projects, and you're going to learn, I think, hopefully very quickly that through a method that Brady has helped make more clear, you can solve any graph problem you come across. There's nothing to be intimidated about. There's no reason to be intimidated by the fact that the sprint is longer this week or anything like that. This is just like any other data structure. We can approach it systematically, and we can solve the problem just like we can any other problem. So the first question is, what are graphs? And I've got the page to your repo opened up on the screen share, so it's kind of spelled out right there. But Graphs are a collection, I'll just read right off of it, of related data. They're like trees, except connections can be made from any node to any node, even forming loops. The nodes in a graph are called vertexes or vertices or verts for the plural, and the connection between the verts are called edges. And edges denote a relationship or linkage between the two verts. We will cover that a little bit more in depth right now. Somebody give an example of a graph that is not listed on the screen. On the screen, we're talking about a collection of cities and linking roads, a collection of computers on a network, a population of people who know each other, trade relationships, and so on. What else could be a graph? Some people type. Lots of things, simple things come to my mind real quick. But I've done this unit before, so. What could be a graph? What's a real common thing that we all probably use every day that's a graph? Exactly, a social network is a graph. It's a very complex, often somewhat dense graph depending on the network, but that's probably like the take-home classic example of a graph is the social network, and we will specifically code out a small social network as an example later on this afternoon or this morning probably after our break. What else is an example of a graph? Think of it like something that's linked. Game of Thrones families, from what I know, I've never seen it, but I think it could make a really good graph. Anybody else? One more person, come up with something that could be a graph. Remember, it's just got to be data that's related. It doesn't have to be computational like, we've shown here on the screen, like Amber's pointed out. Was the finale crazy? I even saw something about it on CNN, but I'm a little distanced from television, so I have no idea what goes on with that. What else could be a graph? While people are typing, I'm going to go ahead and keep moving. We're going to go back over the terminology that we just talked about. So with a graph, as you can see right here, you could have directed or undirected. With a directed graph, as you can see, this data node, this data point, is directed towards this data node. This data node is directed towards this data node. In an undirected, they both point at each other. So think of it like Twitter. You can follow somebody on Twitter, but they don't have to follow you. Think of it like GitHub. You can, I don't remember the terminology right now, but you have your followers and then your people that you're following or whatever followers and following. I thought there was something more fancy that they used, but that is directed because it does not have to be unidirectional. An example of an undirected would be like Facebook. If you're friends with somebody on Facebook or most social networks, you both are friends. There's two relationships that exist there, but that you've got directed, you've got undirected. You'll often see them represented graphically, no pun intended, just like that. So another answer for undirected or another term is bidirectional edge. Remember that the links between the data nodes are called edges, and the data nodes can also be called the vertexes or the vertices. Data points, vertices, vertexes, data points. Natural phenomena, cycles like the rain cycle. Yeah, I could think of you could put some really complicated scientific things, Michael, together in terms of a graph, and some of the things we're going to talk about here in just a few seconds at the end of the terminology. But you also have cyclic and acyclic. A cyclic graph simply means that any point in the graph can reach another point by following through. So you can see here, you can reach this point from here because of this arrow, you can reach this point and you can get back to this point. An acyclic graph simply doesn't allow for that. And you could have very complex examples of both of these, but hopefully that explains the general terminology of that. Then there's dense versus sparse. Krebs cycle. Biochemistry. That was my undergrad major. So when I saw that, it's like, oh, cool. An example of a sparse graph would be like a subway map. Why would a subway map be sparse? Sparse meaning the data, the vertices, the vertexes. Yeah, biochemistry is cool. I had a lot of it, and sometimes I miss it, but there wasn't much money or remote work available in it. Sparse means that basically it's looking at the relationship between all of the vertices, between the data points. So in a social graph, for example, if everyone was friends with everyone in a social network, that would be 100% dense. Sparse would be there's 1 million people in the social network and everybody has 10 friends. That would be a sparse graph. Obviously, I don't think there's any hard point, definition of it, but you get the idea. Yeah, the money was definitely low in it. You get the idea, whereas a dense graph could be like a route map for flights, where you have these different airports and you have a lot of interconnectivity between these airports. And the last is weighted versus unweighted. So with a weighted graph, there is simply a value, an integer normally assigned to each edge, the connection between the vertexes. So here you could have, let's say, it's not being, you could have a 9 here, and you could have a 2 here, and you could have a 1 here. It's giving a value to that relationship. A lot of times a graph will represent those by the length of the edge graphically. Obviously, down to the zeros and the ones, there is nothing of that type that exists. But when you're graphically representing them, you can represent distance. Like, say you were going to represent distance between 2 points on a map. Say you were to represent, somebody was talking about the rain cycle, the average amount of rain in a specific area, however you had decided to link the data and show the data in your graph. So directed and undirected simply being unidirectional. Bidirectional is undirected because there's a relationship like Facebook where one friend is friends with one person and that person is also friends with them. You have cyclic versus acyclic, whether you can reach each data point from each data point. Dense versus sparse, we talked about the subway versus the airline path, and then weighted versus unweighted. There's simply a value assigned to them. Is everybody clear on that? Does anybody have any questions on that? If anybody has any questions, type them now, or we will move on. Anybody have any questions? So I'm going through. If you already don't have it, I'll drop it here in the channel, and I'm going to wait for Jacob's question. This is your repo for the day. Jacob asked, are all these verts usually represented by class instance objects like nodes in a search tree? If you have classes available in whatever language that you are using to implement these data structures, they are I hesitantly say the gold standard. They're definitely the norm that you will see. Obviously, you don't need them, but it's very advantageous to be able to instantiate a class like that, in terms of efficiency, in terms of clarity of what is going on. Obviously, if something like that is not available in the language, you've got to deal with it in a different way. But everything that we do in Python here is going to be class instance objects when we're dealing with data structures, when we're dealing with graphs, that we possibly can do. Does that answer your question? Cool, cool. The link that I dropped, if you go to that link, and I think actually if what I'm at that I'm looking at specifically that I'm following is right there, so it's just a little bit into there, but if you don't already have that information or want to follow it. So the two different types of representations of a graph are an adjacency matrix and an adjacency list. Everybody can see here. So you have an adjacency matrix and adjacency list. With an adjacency matrix, you basically have a two-dimensional array, if you would, a list in Python, and you have zeros and ones, zero indicating no, one indicating true or yes. So there's a B. There's a relationship from A to B. And then, of course, BA will also have a relationship. And each point for each relationship, each possible relationship, is represented in an adjacency matrix. On an adjacency list, as we can see, and they've got X and P, the graph here, X and P, the vertices, the vertexes on the graph represented in the orange here on the adjacency matrix. The adjacency list, in this case, uses a dictionary and sets where you have your key and your values are simply put into sets. Anybody think of why you would put your values into a set as opposed to something else specifically? Or maybe a more general question, can anybody think of any pros and cons of an adjacency matrix versus an adjacency list type of way at that? What would be pros and cons of a list versus a matrix? If the edges are weighted, the list can be index sorted by weight. That is a great thought. I've never thought of that before. Actually, the reason, and I didn't because I kind of messed up a little bit. Generally, an adjacency matrix is represented by zeros and ones. However, the adjacency matrix is not confined to that. So you could, with a weighted graph, and it's actually the case where an adjacency matrix makes more sense because we want to be able to use a set with the adjacency lists here in Python. And the reason is, it's a little bit obscure, but we'll cover that more in depth later on. A set can be accessed in one time. So we don't, if we have a very dense graph, if we got a social network with 10 million users and person B is friends with 5,000 people, let's say, we'll be able to access a relationship in constant time and not in linear time having to traverse over a list. If we put, when we call it an adjacency list, it's not a list in the classic sense of a list like an array, whereas for the matrix it is. So two different ways, a way you could do it is you could actually make a set, and then each point in the set could be like, we discussed this on Friday, could be like A9. It could be a object or a set in itself. But on an adjacency matrix, you simply could make these numerical values or whatever you wanted them to be. Is that clear? Anybody have any questions about that? I'm realizing, thinking back on how I described it, there may have left some ambiguity or some questions. So we are going to be using adjacency lists. Almost always you will come across adjacency lists. I've never come across an adjacency matrix. Brady said he's never come across an adjacency matrix. I have seen a suggestion that a matrix is more efficient in terms of the data structures used to implement them. If you have an incredibly dense graph where, let's say like the social network, where everybody is friends with everyone, then a matrix, because of how it's accessed, is a bit more efficient. But in practice, I think you're almost always going to see a list, and we're going to be working with lists here. So just a quick, does anybody have any questions about any of the terminology, directed, undirected, cyclic, acyclic, dense versus sparse, weighted versus unweighted, pros and cons of an adjacency matrix, what an adjacency matrix is, any general questions about graph that aren't necessarily Python related or Lambda related? The other reason that we access the sets, that we prefer a set, is they're unordered. And kind of by, not default, what's the word I'm looking for? It doesn't have to be that way, but it represents it well, because obviously these, let's say in a social media, the friendships are unordered in general. Especially, I mean, I guess you could order them in terms of how long you've been friends or something like that, but by the very bare nature of the relationship, they are unordered. So B and P could easily be put as PB, or XB could be BX. It doesn't have to follow a specific order. And sets, if you didn't already know, and like I said, we'll cover that more in short time in the lessons coming up about sets, but just know that they're unordered. They can be accessed in one time, and you'll learn exactly how these work in a few weeks when we cover hash tables, because this, in a way, is a lot like a hash table. So we'll do some quick coding here, and we are going to implement an adjacency list. So as Jacob asked earlier about classes, we are definitely going to always implement these as a class when we can. I've got the first bit of code here because I was wanting something to say. So we're just going to have a class of graph and our typical Python init statement for the boilerplate of the language. We will say self.vertices, and we will make that empty. So what should we be able to do with vertices? As I just typed without thinking. We should be able to add a vertex. If we were going to add a vertex, other than the Python self that we need to put in there, what else would we need to add if we're going to add a vertex? What would we need to add if we were adding a vertex? Need to add some sort of ID for it. It could just be numerical. It could be a name, depending on what we're doing. And we'll say self.vertices, the vertex ID equals set. What else would we be able to, what else would we want to be able to do to this adjacency list? We can add a vertex. What else do we need to be able to do here? Somebody type. We can add a vertex. What else do we need to be able to add? Thank you, Amber. An edge. Exactly. if we were going to add an edge, what information would we need about that edge? Somebody type, what information would we need about that edge? Independent of anything else, if we invoke this, what do we need to know? If it was weighted, yes, we would need to know how long that edge is. If it was weighted, we would need to be able to assign it a value. But for any edge that we have, because they don't have to be weighted, what would be something we would need to know, a basic piece of information to add that edge? Remember what an edge is. It's one or bidirectional. Let's say we're going to add a bidirectional edge. Yeah, what vertices it connects. So we can just say V1, V2. And then in here, we'll just say if V1 and why is that catching? And this is just an error catch. It's checking to see if those vertices exist. And it's adding that edge. And I was just trying to figure out why I was throwing those errors in there. But it doesn't matter because we're going to start on, this is just a quick example that we've got here. So I'll drop this piece of code into the channel. Adjacency list implementation. Can everybody hear me okay? Oh, that's odd. It's not letting me upload. Thought maybe something was wrong with my internet. I have no idea. I'll try to upload it. There you go. Thank you, Michael. I have no idea why it's not letting me upload code snippets right now. Maybe that was it, but yeah, it could have been my internet. As I said a while back, my internet is shaky at best here. So the next thing we're going to talk about is a breadth first and a depth first traversal. Everybody has hopefully seen that in the videos, so we're going to cover that very quickly. And I'm just going to set something up real quick here. So for a breadth first traversal, we were to open up a graph. I don't really like. What is a good example? There's a good example, has nothing to do with what we're doing, but the directionality of it is good. So for a breadth first search, basically what a breadth first search by definition does is it looks at the nodes that are one away. We're talking about from the root. One away, then all the nodes two away, then all the nodes three away, and so forth. So the easiest way to look at a breadth first search for a graph is kind of like a tree, where it's going to do the same thing, that it's going to first hit this point because it's one away, and then after it hits these points, then it's going to hit the next level. Then it's going to hit the next level. It's doing the breadth first search covers each level, and it completes that level before it moves to the next. A depth first search looks at a neighbor, then the neighbor's neighbor, then the neighbor's neighbor, then so on. So you look at a depth first search looks at a neighbor, then the neighbor's neighbor, then the neighbor's neighbor, and it keeps going. Something to talk about, a difference between a traversal and a search. A search is looking for a particular value and terminates if it finds that value, or at the end if it doesn't find that value. A traversal traverses the entire graph. Traversal walks through an entire graph in the depth first search or the breadth first search order. The search will look for a node and return a path, usually, is actually what it does. So is everybody clear from the videos and from really quick talking here and looking at a representation that what a breadth first versus a depth first search is? See, Kayan is typing, so cool. Anybody have any questions before we move on? And in here, in your repo, there's a lot of good information, a lot of good graphical representation and descriptions regarding the graphs. Breadth first search, depth first search, randomness, connected components. So you've got a lot to look at later on. So if we were going to do a breadth first traversal, and we were going to pseudocode that out, we could say def breadth first traversal. We need a starting vertex. We don't necessarily have to start at, like we looked at trees last week, we don't have to start at the root. We can start from anywhere in the graph, a breadth first or a depth first traversal. We're just simply, we spoke in terms of the root, if there's a root, or position A, or whatever it wants to be, just for clarity. But to be clear, you can start from any point in the graph. So if I was going to pseudocode this out, if you're going to use a breadth first traversal, would we use a queue or a stack? Not the most intuitive question, but would we use a queue or a stack? Yeah, create an empty queue. Remember, the queue is first in, first out. Make this a little bit bigger. Create an empty queue, and on queue the starting vertex ID. And the next thing we would do is create, I'm going to go ahead and go through this kind of fast because we've got so much to cover, but we've got a lot of coding to do that we will do as a group. So we'll create a set like we talked about to store the visited vertices. While the queue's not empty, you're going to dequeue the first vertex. We'll say that vertex has not been visited. Remember, we only visit a vertex one time. It has not been visited. Then we will mark it as visited. And add all of its neighbors to the back of the, and hopefully while we're coding this, that will become more clear what we're doing if it's not clear here. Okay. So if we look back, here at this graph, if we were going to traverse this graph with breadth first, let's just like we did earlier, on cue the starting vertex ID. So we would on cue this one. And because there is nothing else in the queue, what would we do? We would dequeue the first vertex. So we would dequeue the one. We would check if it's been visited. It's not. We would then mark it as visited and on cue its neighbors. So its neighbor, the only neighbor it has is 2. Yes, 7 connects to it, but it's unidirectional. So its neighbor is 2. So we will on cue its neighbor. So we now on cue the 2. And we just repeat that until we're done. So if we on queued the 2 and followed the same process, then we would dequeue the 2, check if it's been visited, mark it as visited, and on cue its neighbors. What would the neighbors of 2 be? Somebody type. What would we on cue next? Yep, 3 and 4. And then we would just continue that process. And with a breadth first search, looking at this process, would we be able to do this recursively or not? Yes or no? Breadth first and a depth first search. With a breadth first traversal, excuse me, I keep saying search. Could we do this recursively? Amber's typing. Let's see what Amber says. You can implement a breadth first recursively, because think about it. You're at 2. Now you've got 3 and 4. We can dequeue 3, we can DQ 4 and start looking at its neighbors at the same time. It might be a little bit more clear later. You cannot do this with a depth first traversal. But you can do it with, you don't have to do it recursively, but you can do a breadth first traversal recursively if you want. You cannot do a depth first. And we'll go back here. So if we want to create an empty queue, we would just say queue equals and create that queue. And to create a set, we would just call that visited equals so what would we maybe do right here while the queue size is not empty? What could we do to check to see if the queue size was empty? And keep, yeah, we could, we'll check, we'll assume there is a, we can just say while queue dot size, there's a method for size, but yeah, you could, it's greater than 0. And then we're going to DQ the first vertex. So we would just say B equals, and assuming we've got this underlying data structure in there, we could DQ. If that vertex has not been visited, we'll just say, is it in visited? So using Python syntax for the visited that we have created, you can import the queue over here in SQ. I've got the, so we've got the on queue that I should have just shown this, and I'm going to go ahead and drop this code as well, this starter code. For a stack and a queue. I have no idea why it's not letting me. I'm going to go back to this real quick. I'm going to give everybody a break in just a second, and I'm going to figure out. So if we want to mark it as visited, we'll just say print v, the vertex, and add all of its neighbors. So you can say for next vert in self dot vertices. And on queue, the next vert. Anybody have any questions about what this is doing? We have the pseudocode. We have a queue, an underlying queue here that I'm going to get to you that's just got an on queue, a DQ, and a size. And we're simply making the queue on a Python list. And then we've got the same for a stack, but of course we've got push and pop for a stack. And then for the breadth first traversal, we're simply instantiating the queue, on queue the starting index that we have supplied here where we want to start traversing, creating an empty set for visited, traversing while the queue, the size of the queue is greater than 0 while we still have these vertices to visit. Going to DQ. If the V is not in visited, there is a chance it could be in visited. Keep that in mind. Then we will mark it as visited. And then for the next vertex, we will on queue it like we talked, and it will repeat this process because we're calling the on queue. And this while loop is running while the queue. So any questions about that? I'm going to give everybody a 5-minute break, and I'm going to restart my Slack to see if I can be able to post these code snippets. So if nobody has any questions, we'll meet back here at 8 after the hour. So your time or Lambda time at 10:08. We'll meet back. So I'm going to pause the video real quick and let everybody. All right, everybody should be getting back right now. So I dropped. Cool, Michael. I got your message. I saw you were typing earlier. No worries. I'm going to share my screen again. I went ahead and just posted the code for depth first traversal because we've got a whole nother part to cover and we're already an hour into this. So for the depth first traversal, it is basically the same code that we have for the breadth first traversal, but in here we import the stack, and instead of a queue, we use a stack. Remember, a stack is first in, first out, and because of the depth first traversal, the fact that it's traversing the neighbor of the neighbor of the neighbor of the neighbor, if you're thinking of it like a traditional representation of a tree, remember, instead of going through each level, left to right, as you might think of it, we're going from the top to the bottom, from the top to the bottom. It's penetrating the depth of each possible route first. Because with the depth first traversal, we don't know if we visited those yet. That's why you can't use a depth first traversal recursively, whereas a breadth first search works recursively because of the way that the direction that it traverses. So like I said, with here, we're just instead now with the dropped this code with the stack. Of course, we've got a push and a pop method. We're simply pushing to the end of the stack. We could keep pushing if we wanted, and then finally we pop the last value that we've added to the stack. So that code is right here. And then we've got the breadth first that we walked through, the depth first, which is the exact same that I've got here. Besides, we have replaced Q and the on Q and DQ with push and pop. And we've got the same while loop, we've got the same visited, and we've just replaced the queue with a stack. Anybody have any questions over this? You're going to get a lot more repetitions through this in your independent project, but between the video and the live coding, we wanted to cover the basics of this today. So we've been talking about a traversal. One thing with a traversal is, like we said, with it traverses the entire graph, whereas a search generally is going to look for a specific value. If it doesn't find that value, it will return something, -1, 0, a message letting you know that it didn't find that value. If it finds the value, generally it returns the path. Can someone think of, with a search, then if we're looking for a path, something we've got to do different here than this? Let's think about this breadth first search that we've done. If we were going to do a breadth first traversal, if we were going to do a breadth first search, what would we have to do that would be different than the traversal? We're going to have a starting vertex still. We got a target value, obviously, that we're looking for, but what else would have to be different? Somebody type. With a search is returning a path. So if we're going to return a path, what would we need to do different than what we did in the breadth first traversal, where we were simply traversing through, keeping a list or a set of the visited, and if it was not visited, marking it as visited, and then on queuing its neighbors? What would we have to do different with a search if we're returning a path? Everybody hear me okay? Somebody type? Okay. So with a breadth first search, we would want to actually we would want to save the path. So if we were going to do a breadth first search, we would create a queue, instantiate that queue, on queue the starting vertex ID, have visited in our set, instantiate that set, and a DQ as we did before. And we're going to set V equals to the path, then -1. The V is not in visited. What would we check for at this point if V is not in visited? What would we want to check for? We're doing a search. We've done the same with the queue. We've on-queued the starting vertex ID. We've set up a visited set. We're doing a while loop to traverse the graph while the queue.size is greater than 0, the path, and then we're going to dequeue. We're creating a path. We're saying V equals path to the -1. If V not in visited, what are we going to do? What are we going to check for? Yep, we're going to check to see if V is the target. So we can just say if V equals the target value, then we return the path. And here we add to the visited that vertex. So we're checking if V is the target value. And if V is the target value, right here, we return the path and we terminate. So we're saving the path. And returning that path if V is the target. If it's not the target value, we're simply adding V to the visited, and we're doing the same as above for next vertex and self.vertices. And we're going to create a new path. Create a new path with that list that we've already made for the path. The new path, we're going to append the next vertex, and then we're going to on-queue the new path. Everybody see what we're doing? We're doing the same thing what we did with the breadth first traversal. We're traversing across the graph, and we're looking to see if we found the targeted value, but we're building a path at the same time while we're doing that. So when we run this whole code, once it finds that path, the breadth first search finds the shortest path to a value. A depth first search does not necessarily return the shortest path. A breadth first search does return the shortest path to a value. And so we're just building that path based on the next vertice. We're making a new path out of the current path, with making a new list, a new path, and we're appending the next vertex. I keep saying vertice, but appending the next vertex, and then unqueuing the new path. I'm gonna let is V what Jacob typing again. A little confused on why path -1 is referred to on line 27. Wouldn't path just be a reference to a vertex? Why is it considered? Because Jacob, the path that we're saving, remember, the path, we're making a list to keep the entire path. So if, say we were looking for 5 and we were doing a breadth first, we would start with 1, then we would go to 2, then we would have to check 3 and 4, and while we would continue to work here, 3 would then next check 5. We would finally find that path. So the path is having to store each step that we've taken that reaches that target value. So that's why it's a list and not just a single vertex. We're dealing with the vertex below, seeing if it's been visited, seeing if it's the target value, adding it to visited, and then going to the next vertex. Does that make sense? Yeah. Yeah, this is a lot of information getting thrown at y'all, even with the pre-class videos, even with all your previous knowledge, even with what we're going over today. It's a lot of information. So I think, and it's not a cop-out line, I think a lot of it will become more clear, not only as we finish here, but as you start in your independent project today, a lot of it will become more clear. But I think if anything, take home at the beginning of this, you need to understand the basics of the graph, what it is, the different terminology that we've been talking about with the graph: directional, unidirectional, or bidirectional, the vertices, the edges, weighted versus unweighted, cyclic versus acyclic, being able to reach each point, breadth first search, in the fact that we are visiting each level first. A depth first search just keeps looking at the neighbor of the neighbor. So in here, if you did a depth first search and you started with 1, you literally could just depth, boom, I found number 5. Depending on how you were in, then that would actually be the fastest way to find this path. But this path, the depth first, does not always give the shortest path, whereas a breadth first does. I'm going to keep going because we don't have a whole lot of time. But if you've got any specific questions, Jacob, you can definitely message me later and we can go over it in a one-on-one. That goes for anybody. I mean, anybody that's in my TA group, especially anybody that's in my PM group. But I do need to keep moving on because we're already at 20 minutes past the hour. But I think, like I said, some of this will become more clear. So I'm going to grab something really quickly. This is the breadth first search that we just discussed and we went over. I'm going to go ahead and just drop the code and talk through it real quick for the depth first search. Once again, it is basically the same code, but it's using a stack. And remember, these are referring back to the underlying data structures and their methods that we've got here in SQ that I dropped above. So for the depth first search, you're dealing with the same, but you're dealing with a stack, which is first in, first out, or excuse me, first in, last out, while a queue is first in, first out, like a line at a bank. So I think I may have misstated that. It's just making me think of it earlier when I talked about a stack, but remember a stack is first in, last out, because we always are popping off the top of the stack. So if you stack 10 plates on top of each other and then you're grabbing off the top of the stack, you're going to have to go through all those plates to get the first. Whereas in a queue, they would all form a line like a line at the bank, and the first plate that went in would be the first plate that went out when we dequeued. So we were on queuing each of the plates and each one moved up in the line. Anybody's not clear on that, ask real quick, because I'm almost positive that I misspoke earlier about a stack. A stack is first in, last out. A queue is first in, first out. So because a breadth first search traverses each level of the graph, one neighbor further, but all of those at one time, we would use a queue, a first in, first out, because a depth first search traverses the neighbor, the neighbor, the neighbor. It moves down in a classical sense from the representation that we have a graph in. We use a stack because a stack is first in, last out. Remember, a breadth first search finds the shortest path. A depth first search does not necessarily find the shortest path. So for the depth first search, we're just implementing the stack. We're pushing the starting vertex ID onto the stack. We have our visited, our same while loop. Now we're popping off the stack. Remember, taking off the end of the stack. Doing the same thing with the path, the visited, looking for the target value, returning the path, adding to the visited if we haven't returned out. If that vertex was not the target, then we add it to the visited. And then for the next vertex and self.vertices, the same as we've been doing above, we're creating a new path because we're looking for the path with the existing path, and for the new path, we're appending to the next vertex. Be very careful to follow this methodology in your repo. I know last time when we were working through the repos, we had some issues with people that were not creating a new path like this, and for reasons that we can go into more later on, there was an issue with this. So does anybody have any questions over the depth first, the breadth first, the traversals, the search, the queue, the stack, the terminology? Any questions? Any questions? Give everybody about a 2-minute break, and then we're going to tackle this social graph that we're going to make. So at 30 minutes after the hour, I'm going to start again, or 30 minutes, let's say 31 minutes after the hour. So about 2 minutes and 20 seconds, I'm going to give everyone a break. Just grab a cup of coffee quick, stretch. We're going to move on to something totally different. Well, not totally different, but Okay, let's get started again. Everybody hear me okay? Somebody type. Everybody hear me okay? Cool. All right. Okay, so I'm going to go. You have this random social network that we're going to talk about, and I will drop the link to this. And you're going to be doing a lot. Set is a built-in class into Python, right? Not sure. Yes, a set is something that is available in Python. So that is nothing that we created. That's a built-in. It's built into a lot of higher level languages. It is not available in some languages. It's not out of the box. It's just something that's working under the hood. Think of a set as just an unordered list that can be accessed in constant time. There's no indexing to it. So we have, like in that instance, we were using a dictionary earlier for the adjacency. I'm having to think of the adjacency list. So, like I said, it's called an adjacency list, but we were using a key value pair, a dictionary, an object in JavaScript, if you would, for it. And your key was your single vertex, and then your values were all the relationships to that vertex, all the friends in a social network. It's an unordered list, if you want to think of it that way. Does that answer your question, Jacob? Anybody that's got a question, feel free to ask. These are good questions. These are how points come up that people are unclear on. When I don't know that people are unclear on something, there's not necessarily something I can do to help clarify that. So the more questions that you ask, the better. I know we're going through a lot of stuff. But now we get on to social networks. Okay, cool. So nobody else is typing. Now we're going to move on to social networks. Your social graph problem is going to, you're going to implement a lot of methods on that in your independent project. So for this today, we're just going to we're going to talk about the problem a little bit, go over some pseudocode, and implement the basics of creating the friendships, the possible friendships, and being able to add friendships. And you will have to do a lot of other things, such as finding the degrees of separation that we're looking at here. But we're going to talk about generating users and friendships, and something we've already gone over well, but I'm seeing here in my notes that they want pointed out is that the provided code of a social graph that you see right here. Does this look familiar? Does this look familiar to what we were talking about earlier? Somebody type. What does this look like that we talked about earlier? Yeah, it's an adjacency list. Exactly. I'm sorry if I mispronounced. Is it Leanne that you pronounce it? Am I pronouncing that right? You can get on your speaker if you want. I don't want to say, okay, Leanne. Yeah, it's an adjacency list, exactly, that we talked about earlier. Remember, we can have an adjacency matrix, but with a social network, we're not going to normally have a dense social network where everyone's friends with everyone. By very nature, social networks tend to have a lot of people, and an adjacency matrix would take up, have a lot more space complexity, and does not improve on the efficiency whatsoever of being able to look up relationships. In fact, because you have to traverse over that two-dimensional array, it makes it much more complex than if we were to have the sets that we can access in constant time that we'll cover more in a few weeks, like I'm talking about. But yeah, and what we're wanting to be able to do here right now is to be able to create a social network that we're going to represent with a graph and be able to populate that social network randomly based on the size of the social network and the average number of friends in the social network. Did everybody watch the video on connected components? It's a video called Connected Components. If you didn't watch that, I encourage you, before you get around to the social graph problem, that you might want to watch that video on connected components. So remember that, like an extended social network, kind of the friends of your friends, if you would, and that's equivalent to connected components. Because you have your friends, they have their friends, and when we start talking about degrees of separation, it's kind of like the old Kevin Bacon thing of, like, you know, degrees from Kevin Bacon. In this case, we're talking about the social network, the extended social network, being friends of friends and so forth, and being able to find this degrees of separation that you'll do later on involves connected components. So Brady and I talked about it earlier, and Brady said that if we've got a graph problem, the way he likes to think of it is to solve any graph problem, you want to translate the terminology into the terminology that we've just learned this week when we think in terms of graphs, when we terms directed, unidirectional, bidirectional, when we think in terms of weighted or unweighted, cyclic or acyclic. But we talk about in Polya's problem-solving process of being able to understand the problem, ask questions about the problem, and put the problem in your own words. Well, in this case, we're going to stress being able, with a graph problem, being able to put it in your own words in terms of the graph terminology that you've learned this week. And then the second step is build the graph. That's somewhat, you know, in Polya's problem solving, we have understand the problem, you know, create your plan to solve that problem, implement that plan, and then iterate to improve upon that plan. Here we're just going to go to the number 2. We're going to say build your graph. But obviously that's going to involve some planning. And then for number 3, traverse your graph. And we're going to be traversing either breadth first or depth first traversal to be able to do these operations. So you just need to be able to translate it into terminology that we've learned this week, build your graph, and then traverse your graph. So let me go back to code here. We want to be able to, the first thing we talked about is populating the graph. Number of users, we're going to be able to define the number of users. And then we're going to have the average friendship. So we'll just simply say, like I said, if we have 10 users and 2 average friendships, that means each person has 2 friends. Pretty small and pretty sad social network and social graph, but we have to be able to define this, because you real quickly, the more dense a graph becomes, depending on the operations that we're performing on it and how we go about doing those operations and the efficiency of the operation, it can become very, very intensive on time and on memory. So the first thing we want to be able to do is reset the graph. And this is just in case we want to have more than one pass with the graph. Obviously, we need to clear everything out of the memory. So all this is doing is creating users, creating friendships, The last ID is going to be the first friend that in the graph that we're resetting it to. Maybe we were already on 1,000,000 or we were on 10 or we were on whatever. So we're the last ID is simply becomes the first ID, which is 0. We have the self.users and the self.friendships that we have also blanked out. So then after we've reset the graph, if we're going to populate the graph, what do we want to be able to do? Add users. So if we were going to add users here, we're having to generate, remember, we're randomly generating this graph. What do we need to do to add users? Somebody talk. If we were going to add users and we had a number, an integer, number of users, what would we need to do?
You need a random number of users to add?
Well, no. Right here in the parameters, we've said how many users we're going to add. So as we add these users, you have this parameter. What operationally, I'm asking, what would we maybe want to do to be able to add those users? To add to the users here on line 4. Matthew said for I in range num of users. And that is very close to what I was looking for. I will put. And the reason I'm using this is because it's 0 based. So we want to start at 0. And remember, in a for loop in Python, it actually will be n minus 1 for this, the number of users minus 1. You could, Jacob, you could say while index less than num users and traverse from 0 to the final index, so the numbers of users minus 1, and just keep adding at the very end, incrementing your I manually like we do in while loops. Certainly. Remember, I think just about all the time, if you can use a for loop, you can use a while loop. It's just different syntax. Some of them are just more clean and a little bit more short for the job at hand. But yes, you certainly could use a while loop. Good thinking. So we have we're calling add users here, and this will be something that you implement later on in the code to add the user. But know that if we were going to add users, we're going to have a method up above here that we're referring to. And this is going to be something that you'll implement. And then we're just using the user that we're adding in interpolation here. Python syntax. Using that I. And what we get from there. What would we need to do after we added the users if we're making this social graph? What do we need to do after we had users if we're going to have a social network? Yeah, we got to make friendships. So we will say create friendships. Once again, it's something you will be implementing. So we've added users and we've created friendships. Okay, if we're going to randomly populate this graph, if we're going to randomly populate it, what would we have to do while we created friendships? What's the first thing we would have to do? Does anybody have any idea? We want to be able to we want to be able to have a number of users and an average number of friendships per user, but to be able to do that randomly, we've got to have something as a base to be able to do this. What would that be? What would we want to do? If we want to be able to make a random graph, we need to generate all possible friendship combinations. So for this, we could say possible friendships to make a list. And while we're generating, think of it, if we're friends, we have two different relationships. We have A is friends with B, B is friends with A. Remember back to our adjacency list that we can go to here for the social graph. Your adjacency list, A is friends with B, B is friends with A. So what would we have to do if we generated all possible friendships? What's something we might want to check for while we're generating these friendships? Anybody? Everybody hear me okay? So Jacob was typing. Well, we're gonna talk about creating that, but one thing we're gonna do is we want to. What I was trying to get at first, Jacob, but you bring up a good point of whether we're going to do a depth first or a breadth first traversal, and that is when right now we're just trying to actually create the graph. So you're thinking a little bit ahead inadvertently, but in creating the graph, we can do that fairly simple. What I was looking for simply is we want to make sure we don't have duplicates, because remember, this is bidirectional. So once we've created a friendship, we want to make sure that friendship already doesn't exist. That's both practical to here and practical in a real social network, to be able to not be able to friend someone that's already a friend. That's already kind of occurring up under the hood. But for that, we'll just say avoid duplicates by ensuring first number is smaller than the second. Remember, we're using integers here. So you could say for user ID in self.users, for friend ID in range user ID. Remember, if we're creating a friendship here, we created friendships above. So think of that when we're creating the friendship, we're going to have a user ID and a friend ID, just like when we created an edge, we had to have V1, V2. Well, for this, we have user ID and friend ID as the same thing, because we have to have those two vertices to create this edge, this friendship, this relationship, this bidirectional relationship between these two data points, between these nodes and these vertexes, as we would say. So we'll say for friend ID and range user ID plus 1, self.last ID plus 1. Typo there. And so we're just creating a possible friendship with the user ID and the friend ID.
Should it be for user ID and self.users, not user?
Yes, you are correct. Good catch. Sorry about that. That was a typo that was unintentional. Sometimes when I do these, I'll put intentional typos in, but they're not going to be typos like missing an S or missing a semicolon or something like that. They'll be intentional errors that I throw in when we're working with code like we did a few days ago, where we're actually running the code and seeing what the results are and throwing errors. Sometimes I'll introduce things, but definitely speak up. I forget semicolons at times. I'm going to make typos. Sometimes the computer catches it like it did here with what I had the B and the L flipped up. But yes, definitely for user ID and self.users, and then for friend ID and range, user ID plus 1, self.last ID plus 1. We're just appending the possible friendships and user ID, friend ID. And did y'all get a video about randomness or not? I think I dropped that video. Yes, see, or as we would say here in Portuguese, sim. So something now that you basically, it's because we're trying to be able to randomly generate this graph, because you have randomly created all the possible friendships, and by the nature of how we've done this and how you're going to expand on that and do it later, what the parts that we haven't filled in here, it's going to be ordered, if that makes sense. So we can't just say, okay, we want to have X amount of friendships and grab that first chunk. So we would want to be able to shuffle the possible friendships. And I think we actually specifically went over the shuffle in random.shuffle, and it's throwing this because we didn't import random up here. So you're going to shuffle the possible friendships. Remember that you might want to look back on random and some of its basic methods in the shuffle in the Python documentation. If you're using a number to seed it with, look over remember initiating the seed like we talked about. It was the random.seed and the parens that we used the other day. But for here, we'll just talk about random.shuffle possible friendships. So once you've made all the possible friendships, you're going to shuffle the friendships. And then now that we have a randomly ordered list, we can actually create friendships for the first X pairs of the list. So for this social graph, we reset it. We added users based on the number of users that we're going to have, and based on a method that you will implement for add user up on lines 8 and 9. And then we're going to create friendships by generating all the possible friendship combinations. We instantiate that list. We avoid duplicates by ensuring the first number is smaller than the second number. So there's going to be some work in there that also needs to be done. Then we're going to generate all the possible friendships while avoiding those duplicates, line 14, 15, 16. And we're going to shuffle those friendships. And then based on the first X pairs of the list, we will say X. We're going to actually create those friendships. Remember, we've got unique friendships here. We made sure that the first number was smaller than the second, which may make more sense when you go back and do this. But we're ensuring that we don't create duplicate friendships. Once A is friends with B, we don't have to create a friendship between B and A. So the X is determined by the formula number of users times average friendships that we have above here. We're going to say // 2, which 4 is the number, to the next lowest integer. Why do we have this formula? X is determined by the formula number of users, the number of friendships that we're going to create is the first X pairs on the list, this random shuffled list, this random list that we've created by shuffling of possible friendships. And we're going to grab the first X amount to be the actual friendships that we're creating for this graph. Why is it the number of users times the average friendships divided by 2? Somebody type. We have users. We have friendships per user. We multiply that out to get a number. Why would we divide by 2? Yeah, 2 people share one friendship. So we're just in selecting how many friendships we need to be able to reach that average number of friendships. We simply divide by 2 because we only need half that number of friendships that we've generated. The first X pairs will be half of the number that we're coming up with of numbers of users times average friendships. So if we have 10 users and we want 2 friendships per user, that's 20, but we only need to create half of that number because each friendship is a two-way thing, as Michael says. So for this, we could just say for I in range num users times average friendships by 2 friendship equals then we're going to have an add friendship. That's going to be another method. So you're going to be creating add user, add friendship, same thing as add a vertex, add an edge. This random.shuffle is available through Python. Remember, you need to import the random at the top. And I would look at the documentation a little bit for the random. Possible friendships is just the list that we're creating when we create every possible friendships, and we're appending it here. That is a method available through Python. User ID, friend ID is the same as v1, v2 in the code we did earlier. Just the two vertexes that we're creating an edge in between, the bidirectional nature of the graph for the friendships in a social network. Remember, these are going to be parameters that you take in while you're creating all these possible friendship combinations. And then you just have your for loops. Anybody have any general questions about what we're starting to lay out here? Any questions about the terminology, breadth first, depth first, efficiency of them, when you would use them, what they can be used for, the social graph problem that we're going to be dealing with, what you're going to tackle with that problem? And like I said, a lot of this is pseudocode in here that you still need to be able to build on. It does reference some methods that you need. I think I tried to go over every single method and whether that was included or something you needed to generate. Went over the parameters or the variables that we're referring to and where they're coming from in your code. There's the starter code for that. We're already running over. It is unfortunate that we don't have more time to cover this. Really, it would be nice. We've got 4 pieces to cover, and we cover 2 parts per day today and then 2 parts tomorrow. It would be nice if we had all week to do this, but then we wouldn't have the appropriate amount of time for the sprint that they've laid out. Hold on one second. Let me look. Where is the append syntax on line 15 where there are 2 vars and nested parens? Is this appending 2 things at once? So oh, Jacob, so what we've got is it's just appending a set into the list. So you've got your list here, and it's just appending a set and then giving the parameters. Remember, we represent the set with parens. So we're appending a set into the list. Remember, the list can take any type of data type. So we're appending a set AB. It's unordered, like we talked about a set being earlier. Remember, we talked about an adjacency list being a set. So you might want to go look that up. The sets. I think that's honestly, of all the things, and I'm not saying anything about the question because I love getting questions, because like I said, that's really the only way that I can gauge what people are understanding, what people aren't understanding. And in general, if one person doesn't understand it, at least half the people don't understand it, if not 3/4 or 90% or 100%. So you can go to the documentation here and read about a set if you want, the official Python docs. But in all honesty, and maybe it can word it better than I do, I mean, right there, a definition that comes up at the top. A set in Python is a data structure equivalent to sets in mathematics. It may consist of various elements. The order of elements in a set is undefined, as we talked about. You're accessing these elements in constant time because of something that we will talk about in a few weeks with hash tables. You can add and delete elements of a set. You can iterate the elements of the set. You can perform standard operations on sets, union, intersection, and difference. You can look those up. Those are actually built-in methods for Pythons. I remember somebody found that and used it kind of impressively in the code challenge or the sprint challenge last week. They used intersection to find that, and it was legit because it didn't prohibit using that. But that's something that's a little bit beyond the discussion today. But just remember, it's if you think about it like an unordered list, it's this data structure that's holding these elements, but there's just no indexing and ordering to it. The reason we're able to access them in constant time is because under the hood, they are a hash table. A hash table we will go over in a few weeks, but without creating more confusion, I think a real simple way of describing it is that for each key in the key value pair, remember this is just a set. Each of these is a set. So this is a key. The value is the entire set of whatever length of, in this case, the friendships that we have. With a hash table, its underlying data structure is a list. And with that list, you actually run the key through a hashing function and it tells you which index to go to. When you go to look it up, you also run it through that same hash function, which is a pure function, as we have talked about long ago, I think, in JavaScript. It's always going to return the same value. So it's going to tell you which index to go to. And in telling you which index to go to, you automatically, it's represented a little bit different than in here, but you automatically are able to access it like that. But don't worry about that right now. Just for right now, worry about that in a set, we can access that in constant time. We can add and delete in constant time. We'll cover why of all that later. That set is just like an unordered list. Is that more clear, Jacob? The link that I put and kind of what we looked up? But it's the terminology itself is all based on mathematics. Cool. Dropped you all the code we've done today and the code that we didn't type out that I walked through. You've got your repo for the short week, and then we will have the sprint on Wednesday, as we discussed. We will have another GP tomorrow where we'll go over parts 3 and 4. If you haven't finished those videos, you need to finish those videos, and I will take any more questions that you may have here. And remember, I dropped all I know Elvis drops them in the main channel. I dropped all the videos that you should have in this channel and pinned them. So you had your in photographs, breadth first, depth first, connected components. Had the randomness that I added, and then the project that we had today. Your independent project. So if nobody has any more questions, I am going to end this. I will get the video posted. I have all your code in. You've got your videos if you haven't finished them. You've got your repo, the layout of the week. Like I said, I encourage you, the 20-minute rule. Look over this material again if you need to. Adhere to the 20-minute rule. Use the help channel. Reach out to your PMs if you have questions. and I'm going to turn you loose for lunch. We've already run 10 minutes over. I apologize about that. Tomorrow will probably be the same. We've got a lot of material to cover. But then the following weeks, we go back to the same format, 4 days of GP and the single day 3-hour sprint. Anybody have anything else after this marathon of a day? All right, I'm going to go ahead and end this, and I will get the video posted as soon as it processes and I can get it uploaded to YouTube, and I'll drop the link in the channel. And if anybody has any additional questions that come to mind, remember we have lunchtime coverage and the PM off time hour coverage. So there's always somebody in the help channel. You can reach out to your individual PM. You can reach out to me with any general questions or any more specific questions. So thank you.